test level one.
You did the.
No, we did the one where the two boxes were on the slope pull on them.
Yeah, double ramp.
Oh.
The last one does
I can't wait to run this.
That, okay. Oh, okay. Go to master set.
Let's talk about friction. There are two theories about friction, and we're potentially in a transition period or potentially in a period where eventually they'll come out and go, we don't really care about the new theory, the old one works fine. And it's primarily because engineers are practical, they have something that works, it's good enough. Physicists usually don't deal with friction. So, in the two models of friction, we have one model of it. So if I look at the friction versus the applied force. So as I push on this table, I hope that you can accept the fact that it is not sliding because of friction. I push more force, the friction is matching me. The friction is going to match until I reach some sort of breaking point. When I hit that breaking point, then it becomes easier to move, unless you're running into a wheel. So in this first theory, the way the book does it, the way most textbooks have it, is that the friction will match whatever the applied force is until you reach a breaking point, at which point the friction goes to some steady value. In this region right here, this is static friction. Generally symbolized by the F with the subscript S. And over here, this is kinetic friction. Some textbooks will call it sliding friction.
What's the subscript of force?
That's an S.
No, the.
Oh, APP for applied.
Okay.
Now, because this is a constant here, it is dependent upon, it's got to be dependent upon something. So first off, what would friction depend on?
Contact.
Okay, it does require contact. What else would friction depend on?
Force.
What'd you say?
Force.
Force?
Desired force of motion.
Force is a rather vague term. And desired force of motion, I'm not quite sure what that means.
It's a fancier version of force.
Do you think the table would be easier to move over the carpet, or this box would be easier to move?
Mass.
Wait,
What?
what are the choices? Which would be easier to move over the carpet? The table or the box?
The box.
Why?
Less friction. Or
Less Sarah.
Why? I'm trying to get to why would it have less friction?
Because it's not as big.
The weight? All right, so if it's the weight, so I'm going to push on this. Now Newton's second law, F equals ma. Once I give this a push, if the total force on it is 0, the acceleration would be 0. So once I get it moving, it should keep moving. It stops. Therefore, there must be some force causing it to stop. And hopefully you can accept this force that caused it to stop this friction. So I'm going to apply a force to it. It slides that far. Have some sort of sense in your head about how far that is. I'm now going to put this on top of it. Try to push with the same amount of force. It didn't seem to go as far.
And the thing on top moved, or tried not to move, rather.
Now, did the weight of the box change?
The box didn't. The overall weight did.
But the question is, the friction is between the box and the table. Did the weight of the box change?
No, but the normal force between the box and the table did.
And that is the difference. Friction does not depend upon the weight, it depends upon the normal force. So one of the factors, let's start out with kinetic, is equal to something times the normal force. Now, if I did I'll do it this way. There we go. All right, so I have box sitting on cart. I push it, it stops. Friction stopped it. Suppose I reversed it. Will it stop as fast? Same.
The same.
Why are you different?
Why?
Because like
Texture?
Yes, there we go. The texture.
Okay, so the texture of the surfaces, you're speculating makes a difference, and it should. So we need to somehow, how do you capture texture in a formula? Well, you find it experimentally, and then you use the letter mu. It's okay. This mu, right here, mu, mu, it's like a U with a stem up front. The mu is the coefficient of friction. With the subscript K, it's the coefficient of kinetic friction. Sometimes I will say kinetic coefficient of friction, but I think properly coefficient of kinetic friction. It is dependent upon the surfaces, plural. If you were looking up the coefficients of friction online, you would need both surfaces. It's not going to have a value for wood on aluminum or something like that. So then this brings us over to the static. We have this maximum value here. This would be Fs max. And so that's going to be dependent upon the coefficient of static friction. And so we have this Fs max is equal to mu sub s times the normal force. And, or we can write it, I'm not quite sure how I keep doing that, but F sub s is less than u s y. Because it's going to match me until I reach the breaking point. I think part of the theory here is that if you imagine normal force is some sense of how tightly two things are pressed into each other. So if I've got, kind of like a badly made jigsaw puzzle, once I get it moving, I'm now sort of going over the surface of it as opposed to trying to, I don't have to get it out of the groove anymore. So it's all above the groove, there's still a rough surface there, but it's easier. Mu sub k should not be bigger than mu sub s. Well, as sort of indicated here, mu sub s will be a larger number, in theory. The coefficients are typically less than 1. But there's nothing that says it can be. I have seen something bigger than 1, but it's rare. Most of it is less than 1. Rubber on asphalt, the kinetic is I think 27 or so. I think if a car is skating to a stop. Questions up to here before I talk about theory number 2. Theory number 2. Theory number 2 says, yes, mu sub s and mu sub k, they're experimentally found, but there's large error bars. You might say mu sub k is 0.3, but it really is 0.3 plus or minus 0.1. Mu sub s might be 0.35 plus or minus 0.1. There's a lot of overlap there. So there's enough experimental error when you're finding these coefficients that there really isn't any difference. And there's no reason they should be different. And under that theory, if I had my applied force here, where's my friction, it would come up like this, and then it would just level off like that. And under this model, F is less than or equal to y, where there's no distinction between use of S and use of K. I know there is one textbook there's one textbook which pushes that theory. They ignore this. Most of the textbooks I see now that will acknowledge both of them say, we'll give a side note to that theory over there, and then use this. This is what we will be doing. Now, those are very two distinct graphs. It seems like surely they can find, there should be some definitive test to tell the difference between the two. And if it's been done, I haven't found it yet. But it takes a while for textbooks to catch up. But I've done searching for papers and just have not found it. I did find somebody whose senior thesis was looking at this, and there were large error bars, and he really couldn't distinguish between the two. I don't think he did enough trials. And yeah, we're done at 9:15. Okay. So on that note, we'll leave you wondering about the mysteries of friction.